Hi, my name is Ben Zhang. I'm from Worcester Polytech Institute, WPI. The topic for the presentation is Outfitting Mobile Foundry System for Department of Defense Rapid Equipping Force. In 2012, the U.S. Army released a report detailing their goal to become fully sustainability through reducing, reusing, and recovering waste streams, converting them to valuable and usable resources. Thus far, the U.S. Army Rapid Equipping Force has designed and mobilized expeditionary labs which includes 3D printer, CNC machine, and scientists engineers. They want to put a mobile foundry on the front-line battlefield for manufacturing process using recycled and reclaimed materials. Currently, the mini foundry housed in WPI Labs meets our sponsor needs by repurposing recovered scrap material and proposing a sustainable waste cycle while respecting the power and water usage limit to satisfy the Net Zero Sustainability Initiative. As seen on the poster, the steel waste cycle will begin as metal scraps retrieved from the battlefield, which are casted as replacement parts, producing construction materials as a byproduct. After cutting and refining the final casted product, all leftover metal will be reused with the next collection of scrap metal to cast the next replacement part needed. While the current foundry setup, the casting system had yet to be mobilized and materials were spread out throughout the WI lab building. Further, the casting process constitutes a hazardous environment for operators due to the high temperatures and film radiation from the process of metal casting. We are mobilizing a steel casting foundry into a mobile container. The harmful effects of the temperature and metal film radiation become more hazardous. Not to mention, the decrease in workspace impacts the operation efficiency as well. With these downfalls in our minds, the team formulated our project goals and objectives. We accomplished this goal through three primary objectives. First, we modeled our foundry configuration in SolidWorks. We then imported our SolidWorks assembly into Ansys, where we established thermal and ventilation parameters needed to conduct thermal simulation. Lastly, we analyzed the temperature distribution diagram output from Ansys to assess the efficacy of each design iteration. The design and analysis process of our project were completed through multiple design iterations to develop our comprehensive final product to assess the safety of our mobile foundry casting foundry, while also aiming for an efficient layout. In our final design, we separate the whole manufacturing processes into two containers, as splitting it into two sub-processes. Both containers were equipped with heat-resistant coating, desiccant, and explosion relief panels. One container for casting contains exothermic crucible and oven with full ventilation system, and the other one is only for preparation and storage, which contains 3D printer and only with simple ventilation system. The ventilation system is one of the most important parts in the foundry, as there will be lots of heat emitted into the air and thick smoke into the small room during metal casting process. The ventilation system has to make the mobile foundry in the environment to be suitable for workers and avoid any damage to the instruments. We use one air conditioner to intake the air with max speed 725 cubic feet per minute, and there will be one fan on the other side wall to draw out the air, as well as 3 arm power fans on the roof to exchange the air all the time. Besides that, we put one overhead ventilation hood right on the top of the crucible, so it can take out the smoke which generated when melting the wasted metal. The air exchange rate in the container can reach up to 31 times in 1 hour. Although the temperature of the molten metal in the crucible is 1600 degrees, we actually do not use this number directly in our simulation, as during the real experiment, we will put a layer of insulation on the top of the crucible, and heat will not emit into the air directly, based on our multiple measurements in the lab. The upper surface temperature of the insulation is around 450 degrees Celsius, and we use this number for our simulation. We apply the air conditioner blow wind with 16 degrees Celsius. According to this assumption, after thousands times of calculations, we get the simulation result for the foundry inner environment, as you can read the data we get from the graphs at here. The average temperature in the foundry is only around 25 degrees Celsius, and this environment is acceptable, even comfortable for the workers while working in the casting foundry. And then later, we even try to simulate the worst scenario that the molten metal emits heat from 1600 degrees Celsius directly into the air. Under the same ventilation system condition, the general inner temperature environment only rises for a few degrees, and it is still tolerable for the stuffs. In general, after multiple experiments, we draw a conclusion that, in order to better control the container inner temperature environment, lowering the AC's temperatures is more efficient than simply increase the air exchange rates, and the mobile foundry design sufficient accommodate 3 operators to produce the needed solution on site in a 25 degrees Celsius environment.